Okay, so here we go. We are starting in on the lecture. We finished the lab last time. You should be getting that, if you haven't already, into your lab notebook. We're going to work on spontaneous, non-spontaneous rates, slopes, molecular collisions, energy diagrams, and follow up on factors that influence rate. We're also going to do a simulation later. That's why I had you guys get your computers out. So if you haven't got a computer, you need to make sure you get one and get it up and running. Okay, we're going to do that in a little bit, not right now. Okay, so today you should have finished quiz number 8.3. You should be starting 8.3 in your sapling. We are going through Standard 5 Objectives B through D again in the Utah Core. Our objective today is not only to find out how factors affect reaction rates, because we explored that last time, but to do the vocabulary and understand spontaneous reactions, molecular collisions, and energy diagrams. So here we go with your notes. So in the first part of this chapter, we talk about spontaneous and non-spontaneous processes. And you need to be able to understand what that means. Spontaneity basically is how fast or how spontaneous something happens, or non-spontaneous. So if we look at some things, so if you dropped a rock on a hill, would it spontaneously roll down? Yeah, because the slope of the hill would help it to roll. What about climbing a mountain? Is that spontaneous or non-spontaneous? Non-spontaneous, good, because it wouldn't automatically happen. I have to put some energy into it. Okay, what about pushing a rock up the hill? Non-spontaneous, again, I have to put effort into it. And what about skiing downhill? Spontaneous, only me it would be more like becoming a snowball coming down the hill, because I would tumble. We have some interesting vocabulary in this unit, so we need to be able to understand it. The first is exergonic, and that's of a metabolic or chemical process. It's release of heat. So think of when we talk about exothermic, exergonic is just giving off energy. Okay, not just heat, but energy. So exergonic, giving off energy. So what do you think endergonic would be? Taking in energy. It's like endothermic, right? But it's energy. It's not just heat. So this is where we get energy into. Entropy is a measure of disorder. So we say that the universe is heading towards entropy, or full entropy, meaning it's heading towards disorder. In other words, when a tree falls in the woods, it will go towards disorder. In other words, it will decompose. It doesn't automatically sprout a new tree. That takes energy. But pulling it apart doesn't. Stable substances are things that, like it says, are stable. I'm going to move this recording thing so you can see that a little better. These occur at the lowest energy state, okay, and what we call chemical equilibrium with its environment. So these are some definitions that take a little bit, the words that are out there, you've sort of got to put it into your brain a little bit differently, I think. Just remember, the easy way for me to remember exergonic and endergonic is like exothermic and endothermic. Okay, but it's not just heat. You got to remember it's not just heat, it's energy of any sort. And then entropy is just disorder. So if I leave my kids' rooms without mama constantly nagging them, they'll go to total entropy, total disorder. But the minute mama blows a gasket, then the kids put work into getting that cleaned up and putting it back into order. Okay, we okay to go forward? We need a few more seconds. Okay, we good to go? Okay, going forward. So we're going to classify each of these and explain if they're exergonic or endergonic. Do they need energy or do they give off energy? So any combustion process, that means blowing up, heating, anything that has to do with fire. Exergonic, it's giving off energy, right? Good. Okay, perspiration evaporating from the skin. It's endergonic, good. We had to put energy in to get it to evaporate, right? So it's like heating water, like boiling water. We have to put energy in to boil it. Okay, melted lead solidifying. So it's going from a liquid to a solid. Exergonic, it gave off energy to become less or become solid. Okay, any explosive detonating. Yeah, that would be exergonic. It gave off a lot of energy, right? Okay, a car being pushed up the hill from the point of view of the car. Endergonic. I had to put energy into it. Good. So the car itself won't do anything until somebody pushes it. So you got to sort of think of it, they will do perspective things like that last one, where you have to think of it as you were the car kind of thing. Okay? So let's see if we got them right. We get them right? Okay, I forgot that I had put those in. Was that a no? Okay. All right, so describe energy and entropy changes that occur in the following processes and indicate whether the processes are spontaneous under the conditions stated. Thank you. Okay, so on a cold day, water freezes. What about the energy? Endergonic or exergonic? Exo, it's getting rid of energy because it's freezing, it's going to solid. Okay, what about entropy? Is it becoming more organized or less organized? It's becoming more organized because we're freezing it, right? Because it's becoming more organized, we have less entropy. Okay, and I don't remember if I've got these. Decreased energy, decreased entropy. Okay, so what about a container of water at 40 degrees cools to room temperature? What do you think? Ender or exergonic? Is it increasing in energy or decreasing in energy? Decreasing in energy because we're cooling it, right? What about the entropy? Is decreasing in entropy because it's slowing down, molecules are slowing down, and so they're starting to become more organized. So it's not the total clean room, okay, but it's in the process of getting cleaned. All right, what about the odor, thank you, the odor. Odor from an open bottle of perfume spreads throughout the room. Is the energy increasing or decreasing? It's increasing because it takes energy for it to spread out, so it has to increase its energy. And what about the entropy? Is it becoming more organized or less organized? Less organized, good. So increased entropy. So less organized is increasing in entropy because entropy is disorder. Okay? Entropy is the amount of disorder. So if I'm at total entropy, I'm at total disorder. Okay, if I'm at very small entropy, then I'm in order. Okay, so let's classify each of these as spontaneous or non-spontaneous. So we need to be able to use these words that you sort of notice these slides that I've had. We're not just defining it and going on, we're actually having to use them. And that's how it's going to be on the test. Okay, so water is decomposed into hydrogen and oxygen gas by electricity passing through it. Spontaneous or not spontaneous? Non-spontaneous. If it was spontaneous, we'd have a hard time drinking water, right? Okay, explosive detonates after being struck by a falling tree. Non-spontaneous because the tree had to fall to get it to go. Okay? How about a coating of rust forms on a clean piece of iron? That will actually happen. Yep, spontaneous. What about a flashlight emits light when turned on? Non-spontaneous because you had to do something, right? Whipping cream dissolves on a hot piece of pie. Spontaneous, good. So if you're getting these, you're doing a good job. If it's coming to you fairly easy, you're doing a good job. Okay, we got these down in our notes. We're moving on. Okay, in each of the following, organize according to the highest entropy. Now, highest entropy would be what? Highest what? The least organized, the highest disorder. Okay, to the lowest entropy, which would be the most ordered. Okay, so solid ice, liquid water, and steam. Reverse that whole thing, right? So it would be steam, liquid water, and then solid ice. Because solid ice would have the lowest entropy, meaning the most ordered. So we would rewrite this. I don't think I've got it. Nope. So we'd write it steam, water, and ice. And I shortened it up a little. Okay, let's look at the next one. Leaves on a tree, fallen leaves blowing around in the air, fallen leaves raked and placed on a sheet. What's the most ordered? Okay, so leaves on the tree is the most ordered. What's the most disordered? Okay, leaves blown, or leaves in the air. And then leaves raked, right, would be in the middle. And I shortened it a little bit. If you want to just go 1, 2, 3 on top of them, that's fine too. Okay, let's look at this. A stack of sheets of paper, a waste packet full of sheets of paper, a waste packet full of torn and crumpled pieces of paper. What's the least organized? So this one would be our number 1, right? Because it's the least organized. What's the most organized?
Stack of sheets.
Stack of sheets. So that's our number 3, right? And so that means this other one has to be our middle one, which was 2. That one was a lot of writing, so that's why I just put the 1, 2, 3. Okay, let's look at the next one. 10% copper zinc alloy, 2% copper zinc alloy, pure copper. What's the most organized? Pure copper. So this would be our number 3, right? What would be our number 1? What's our least organized? Okay, 10%. So this one would already be in order, right? Next one, coins in a piggy bank. Coins in a pile containing the same types of coin. Coins in piles containing the same number of coins. Are the most organized or the least organized? What? But the last one is coins in piles containing the same number of coins. Is that one most organized or is the one before it? We have a disagreement there. What do you think? What's more important? Okay, so this comes down to you've got to make a decision. So let's do what's the least organized? Piggy bank. Okay, so this one's going to be number 1. Now we got to figure out which one of the other 2 we're going to call the least organized. Or the most organized, I should say. So coins in piles containing the same type of coin, so that could be big piles. Coins in piles containing the same number of coins. I would probably go the way it is, right? 1, 2, 3.
Since there are different numbers of coins, I mean like different types of coins in different sizes, so you can have like a diamond and
you could. So there's an argument for both. That's right. So the last one could be more disorganized because we could have different types of coins. So this one was sort of hard because they needed to give us a little bit more. Yes?
So what if this was on the test?
So that's what you've got to make a call on. So hopefully on the test they would have said coins in piles containing the same type and number of coins. I'm hoping they would say. Okay? So good questions. All right, let's head on. So when we're looking at reaction rates, and we sort of did this last time with our lab, we're going to be looking at graphs, and we're actually going to do graphs on the, I don't know if it's next time or the time after that we do the next lab, where we actually do a reaction rate graph. And we're going to look at the reaction rate. And the reaction rate in that yellow box there is what you need to know. The rate is equal to, and anytime you see a triangle, it just means change. The change in the concentration of the reactants, the negative change, divided by delta T, which is the change in time. So you'll look at the equations down here at the bottom. I'm going to move this record again up to a different place. If you look at each of the things in a reaction, A plus B yields C, you'll notice that A and B will be decreasing or have a negative rate because they're becoming product. And C will have a positive rate because it's appearing. Okay? If we look at A plus 4B yields 3C, notice that we also times the rate by the coefficient. Okay, so we need to sort of see how things disappear and how things appear according to our balanced equation. Guys had a chance to write that down and sort of get an example down, so you sort of know what's going on. I think the bottom one, as far as the reaction rate, probably gives you the best one because you can see sort of how it appears and disappears according to the coefficients.
So the negative change of it.
The negatives will be the reactants because they'll be disappearing, and the positive will be the products because they are appearing. Okay? All right. Going forward. So as we look at a graph, when we have a tangent line, which is what's shown in the red, that tangent line shows us an instantaneous rate. So as we start the reaction, the rate is very fast because we've got a lot of reactants and not a lot of products. As the reaction goes on, it starts to slow down because we're losing the amount of reactants. And as we get towards the end of the reaction, we end up with a flat reaction rate, or the rate becomes zero. The slope becomes zero because we don't have any more reactants to go together. Okay? So that's what the slopes represent. So remember, when we're doing a slope, we take away the x and the y, and we are able to find slope. So we're able to find at a specific time what the rate is. Okay? Hopefully you've had enough math that you can do that. If you haven't, we can go back over that a little bit. Now, a lot of times when we're talking about rates, we're just talking about how relative fast, slow they are to other things that we know. So if we talked about melting butter in a hot pan, which would you give as far as their rates? Very slow, slow, fast, or very fast? I hear slow, I hear fast, I hear very slow. Okay, you're putting it in a hot pan. It's going to be fast. Okay, so go ahead and put fast. What about changing of the color of leaves in the fall? I'd probably say slow. I don't know that I would go very slow. You'll see there's an example that's very slow here in a minute. Okay, what about the growth of a garden over the summer? That's very slow, okay. And then what about the decay of radioactive material whose half-life, that means the time for half of it to go away, is 4 billion years? Extremely, extremely slow, right? Okay, what about the detonation of an explosive once it's triggered? Very fast, very fast. Okay, so you should be able to just look at something and be able to tell me if it's going to happen really fast or very, very slow. Make sure that you look at the other examples in a group before you decide, oh, that's really slow, because we were saying that this is very slow, but looking at we were saying this one was really slow, but when we got to this one, this was extremely slow. Okay, so if they only give you 4 things to tell about each one of them, make sure that you're choosing the right one. Does that make sense? Okay, so let's go forward. So we're going to start calculating. We're going to calculate the average rate of reaction on the basis of the following information. Pure A and B are mixed. So we've got the equation up there, A plus B yields C. And after 12 minutes, the measured concentration of C is 0.396 moles per liter. So what was the equation for rate for C? Do you remember? Isn't it the change in concentration of C divided by the change in time, right? So all we have to do is take 0.396 because C would have been 0 to start with, right? And moles per liter is molarity. And we have 12 minutes. So we're going to divide that through and we get an answer. Somebody get it real quick for me. It can be the change in the reactants too, but since all we're given is C, we can do the rate for C. C is product here. This one would be a positive. If I did A or B, it would be negative because it would be going away. Okay, so what do we get for our answer? The unit would be molar divided by minute. It's what? 0.03. Give me one more. So we'll put a 0. Okay, so that's my rate, average rate over that time. So here on the next one we have pure A, B, and C are mixed together at equal concentrations of 0.3 molar. After 8 minutes, the concentration of C is found to be this. So we can see that C increased, right? So we need to find the change in C. So we're basically going to take the 0.0455 and subtract 300, and we get 0.155 molar. That's equal to our change in concentration of C. Is everybody okay with that? Then to find the rate, what do we need to do? Well, remember, change in concentration of C divided by change in time will give us our average rate. So we've got 0.155 molar divided by 8 minutes. And I should have put 8.00, so that's 8.00. And we get molarity divided by minutes for the unit, and 0.0 what? .194. You'll notice that the rates will usually be small. Okay?
Okay, where did you get the first numbers?
The first numbers right here,
Because I was thinking you do...
right here, and right here. So they said all the concentrations, A, B, and C, started as 3 molar. But after we let the reaction go, we found out the concentration of C was this. So now I can subtract those two and find the difference, how much C changed.
Yeah,
That's what I did this, right.
then why...
Because it said after, that happened all after 8 minutes. So that was my time frame that change occurred. So then I just take the change in the concentration divided by the change in the time, and I've got my rate, my average rate for that. Yeah. Well, I subtracted these two, but I divided these two. Okay. All right, so let's go forward. So here we have a reaction that generates hydrogen gas as a product. The reactants are mixed in a sealed 250 milliliter container, and after 15 minutes, 5.4 times 10 to the negative 2 moles of H2 has been generated. Calculate the average rate of reaction. So if we want it in molarity again, we got to do moles per liter, right? So if we take 250 milliliters and we change that to liters, we have 1,000 milliliters in 1 liter, so 0.250 liters. I've got my moles, 5.4 times 10 to the minus 2 moles. Divide it by liters, because remember molarity equals moles divided by liters. So 0.250 liters. And we can end up with molarity. So they throw that through for me. Remember, it's a change in concentration, so we have to put it in molarity because that's a concentration, or parts per million or something that's a concentration. Mole is not necessarily a concentration. 2.16. Okay, that's our concentration. And if we look right here, that was over 15 minutes that changed. So we're going to now take our concentration and divide it by 15 minutes. And we'll end up with our rate in molarity per minute, 0.144. And we're done. Okay, so that's our average rate. It's not our instantaneous rate. We'd have to do calculus to do a, can't think of what it's called. You know, instantaneous rate, you do the integral. Okay. So let's go forward. Everybody got this okay? Everybody understand this? Any questions? Yes?
So, we're doing the 5.4 times the -2 divided by 0.250. I got 0.216.
0.216? Okay. Yeah, it should be smaller. So let's fix that. So this right here is actually 0.054, right? So we move the decimal twice, so we should end up with a point something. So this one was, whoa, hello. So this one should have been 0.216. Okay, and then that would change this to even smaller, 0.0144, is that right? Okay, good catch. Thank you. I trust you guys to give me the right number, so if you don't agree, make sure you're voicing. And thank you for being brave and voicing in the first place. Okay, so now we're going to talk about some molecular collisions. We have reaction mechanisms, and in reaction mechanisms, what basically has to happen is reactant particles have to collide with each other in order for a reaction to occur. If they don't collide, nothing will happen. So that's sort of like boy meets girl. But the particles must collide with at least a certain minimum amount of energy if the collision is to result in a reaction. Remember that video that we saw with them colliding in the class or in the hallways and up went their books kind of thing? So they've got to collide with enough energy. If they don't have enough energy when boy meets girl, then there's not going to be any conversation going on because not either one of them's brave enough. Okay, or maybe there's too much energy going on and they don't get along. Okay, so they got to have a minimum amount of energy. And then in 3, they've got to, in some cases, colliding reactants must be oriented in a specific way. There's some that they can just collide and it reacts, but others they have to collide in an exact way. So it's like I was explaining to you when we did the little part about the date earlier. If you try and go out to ask a girl on a date and you have your back to her when you're asking her out, probably she doesn't know that you're asking her out, so no reaction is going to happen. Okay, but if you're facing her and looking her in the eye, then probably a reaction is going to happen. Hopefully a positive one. I don't think there's, which one? Oriented is behind the arrow here. So you got to be oriented in the right direction to get the date. So oriented in a specific way. So facing each other. Just waiting for everybody to, I know pens are still writing. Get a chance to write them down. Okay, we good to go forward? Almost. Okay, you're okay. Okay, remember if you don't get this, I will post it on the web. Okay, so then we have internal energy. When we talk about eternal energy, this is the energy in a system arising from the relative positions and interactions of its parts. So that's inside. Internal meaning inside. Activation energy, we've talked about this before. We've looked at this graph before. That's the minimum amount of energy that it takes to get from the reactants to the products. So it's activation energy is that blue area, that blue arrow from the reactants to the top of the curve. So if I'm trying to get over a mountain, it takes that much energy to get to the top, and then I can just roll down to the bottom. With a catalyst, maybe there's a way around the mountain instead of over the top. Okay, so it's the amount of energy that we need to get the reaction going. I think you have to come at 7:30 for the ACT. I think you get let out. That's what we've done in the past. It usually ends like at 12. Okay, so let's talk about this. When we have low internal energy, we have, oops, I didn't get these animated. Okay, we have things that are going back and forth. We don't have much stress back and forth. When we have higher internal energy, we have vibration going back and forth, and it's sort of like a very intense, trying to like a pull back and forth. I can't think of like slinkies. They sort of go back and forth and back and forth and back and forth. What happens is when that higher internal energy becomes so great, remember these would be bound together. These would just be like a vibration barely. These would be going back and forth like in and out and in and out. When they finally get enough energy to break away from each other, that's when we have the high internal energy and we're able to actually break away from each other. And they're actually able to go on and bond with something else. Okay? So it's enough to break the bond. Using circles as shown in the two atom compounds, what happens when they collide. So a favorable orientation. So if I have two molecules, and I'm just going to put something like this up, which would represent like an ammonia, and I have an extra hydrogen over here. Remember that it had its two unshared pairs of electrons. So this would be a favorable orientation for this hydrogen to come in and bond and make NH4. But if I had the hydrogen and I had instead the hydrogens coming this way with my nitrogen here and the unshared pair of bonds here, this is not a favorable one because these are both positives, and so they will actually repel each other and force each other away. So the reaction won't happen. So here the orientation is really important. Orientation does matter if it is a compound that only has one opening or two openings for a specific molecule. If it tries to collide with the opposite side, like you see here, the nitrogen wants the extra hydrogen to come in, but if the nitrogen is faced away from that hydrogen, it's not going to happen. So does orientation matter? Yes, it does. Not in all reactions, but in reactions where we have just one place for the molecule to go, or one place for the atom to go. Oh, I do have another pretty one here. So I'm going to erase this one and let you see this one behind it. This is just with a 2. So you can see here, this is a favorable for a collision to happen because these two will bond, this bond will break. But in this one will repel that one, and that one will repel this one. Even though these two want to make a bond, they won't because this won't break. Does that make sense? Okay. So again, if they're not facing each other, not much is going to happen. If they're facing each other, a lot more is going to happen. Okay? All right, so let's look at some examples here. So which reaction mechanism assumptions are apparently being violated in each of the following scenarios? A reaction takes place more rapidly when the concentration of the reactants is decreased. So in other words, I have a classroom full of 20 girls and 20 boys, and I decrease the girls to 10. The reaction rate of finding dates for those other 10 boys slows considerably, right? So here it's the concentration. What assumption is not doing? Instead of decreased, it should have been increased. If it was increased, then more chances would have been so that the reaction would take place. In other words, I'd put 40 girls and 40 boys in the same room instead of just cutting it down. Okay, on the next one, a reaction takes place more rapidly when the reaction mixture is cooled. What do you think's wrong here? The cooled should be heated instead, because heated makes molecules move faster. Cooled makes them move slower. Okay, the reaction rate of A plus B gives AB, increasing as the concentration of A is increased, but does not change as the concentration of B is increased. What's wrong here? I need one A and one B to make the compound AB. So if I increase A but don't increase B, how can I make more compounds AB? You need to increase both. So does not change. We're going to not do that. We're going to actually say we increase B as we increase A, and we're going to get increased. Okay? All right, moving forward. Back to our lovely energy diagram. We've done this one before. This shouldn't be hard. We need to be able to label all these parts. Do you remember all these parts? Okay, so what was right here? Reactants is where I start. So reactants are where I start. What is the distance from here to here? We just talked about it. Activation energy, or energy of activation. Okay, what about the distance between here and here? This is our change in energy, right? Or change in heat if it's in kilojoules, that tells us it's heat. What was up here at the very top? Does anyone remember what's at the top of that curve? Activated complex, good. And what's down here at the bottom of the curve? Products. Now, if I add some other arrows in here, if I did from here to here, what would that be? That green arrow. What would that be? Potential energy of the products, right? And it's not going to write here in the corner from you very well. That's supposed to say products. Okay, what about if I did a green arrow from the top all the way down to the bottom? What would that be? Potential energy of the activated complex. Good. And then, of course, between the reactant and the bottom would be the potential energy of the reactants, right? So we have now been able to label everything. If I was to actually ask for what is the actual energy of activation, what would you do? Well, to find the energy of activation, you would take the top number, which was 103, and minus where the reactants started, which was 45, and you would get your answer. My brain is not good today, so somebody throw that through the calculator. Should be about 50 something, 60, 58, thank you. And that would be kilojoules. What would be my delta H? To find my delta H, I would just go 45 minus 10, and it actually would be getting rid of it, so I actually would have a negative number, so I should probably do that in reverse. So 10 minus 45, because I've lost it, would be a minus 35 kilojoules. And the negative would tell me it was given off. So because it's given off, this graph is what kind of graph? It's exothermic because it is a heat graph, but we could also call it, what was the other word we learned? Exergonic. Okay, yep, you're close. Okay, so this is exergonic. So I can pull those off. I can also say my reactants are at potential energy of my reactants is 45 kilojoules. Potential energy of my products is 10 kilojoules. My potential energy in my activated complex is 103 kilojoules. So there's some things I can pull off of this graph. Okay, so there's a graph for you. And I think you have this one on your next one page, do you? Go ahead and label everything you can on the next two graphs and see if you can give me everything that could possibly be given from that graph. So off to the side, also give me like delta H, what is E of A, what is the potential energy of the reactants, of the products. The second graph, you're not going to be able to do that because why? There's no numbers. But you can label everything. Let me give you a few minutes and get it all labeled. Okay, I've done one for you. How did you find all the numbers that you needed? Were you able to identify the actual numbers of everything? Is there anything you didn't understand? On the second one, we would just be able to label and not give numbers because there were no numbers on this. So I'm giving you that as a sort of an extra one that you can do. Remember that if there's a lower curve shown, that's with a catalyst. Okay, that's the second way to do it, with lower energy. All right, so now we're going to actually draw our own. So on the bottom one here, we're drawing our own. So let's sort of read what's going on here. To draw the energy diagram, the potential energy of the reactants is 50. So I'm going to count up 10, 20, 30, 40, 50. So this is my 50, and I'm going to put my reactants right here. The activation energy is 30. So I'm going to come up 30, 1, 2, 3, and just put a dot over a little bit, because I know that's where I'm going to go up to. The delta H is negative 20. That means from the reactants, I'm going to go down 20. So 1, 2, and I'm going to come over here, and this is going to be my products. Label all parts of the diagram. So now all I do is I just come up, hit that point, and come down to the products. And then I can go and label everything that we've already labeled. So you need to be able to draw a graph like this and be able to write what's going on in here. So I can then say, okay, from here to here is my E of A. This is my activated complex. From here to here is my delta H. From here to here is my potential energy of my reactants. From here to here, potential energy of my products. And from here to here, potential energy of the activated complex. So you should be able to draw a graph and as well as read a graph. Okay? I'll give you a second if you didn't get that all down. And that would be labeling all the parts of the diagram. Any questions, any problems with actually labeling this and drawing it? Mason, put it away. Okay, going forward. So change in energy, delta E is another name for delta H. What was delta H? What was the name of delta H? Do you remember? So this is actually called enthalpy. So delta H is a special word for enthalpy. It's heat, okay? If delta H is positive, it means what kind of reaction? So if delta H is positive, it's going to end up higher. So it's an endothermic, good. If delta H is negative, that means it's going to be a exothermic. Now, if we weren't talking about delta H, but we were talking about delta E, it would be endergonic and exergonic. Okay? So the only difference is delta H represents heat, where delta E represents energy. So what I'd like you to do now, and I have got a hot link for this if you want to go to your Canvas, there's a hot link on there, or you can just put FET simulation reactions and rates in the Google search, and it should bring it right up. I would like you to take a few minutes and just play with this simulation on your own, thinking about these questions. By adding heat energy to a system, what do you notice about the individual molecules and what it does, and what would you hypothesize would happen if the temperature was dropped? Then drop the temperature, see what happens. This right here, this little thing right here, is where you heat it, so you can increase the heat or decrease the heat there. When both reactants are added to the container, I just want you to play with it. See what happens with the different things. I know I've got it up here somewhere, but I'm not sure. There it is. So you're going to actually play with with different things. So you can choose your reaction over here. You can reload your launcher. You can actually launch things into there, see what happens. You can raise the temperature. You can lower the temperature by putting ice in and see what happens. You can add more things in, molecule to launch. You can launch something different and see what happens. I want you to just play with it and see what you figure out from it. Okay, once you've had enough time playing with it, we actually are done with lecture today. So I will put this back up so you can see it. I'm just going to go here for a minute. Remember that sapling 8.3 is what you need to be working on. So after you finish playing with this, go into sapling and work on that. Okay, questions? Okay, I'll leave this up for a minute and let you just look at the questions that I'm asking you and play with it. Go ahead and talk to your neighbor and see what they're doing, what they're finding out about it.
Are you okay to download it?
Yes, go ahead and download it. It will undownload as soon as you turn it off. If you can't get it to work, then ask a neighbor. They probably can figure it out for you. You can download it, like I said. The minute you turn off the computer, it will undownload it because they're frozen. But after you've played with it for a minute, go ahead and you can head into sapling and start working on your sapling.